and this is something I've been working on for the last about 5 years, and I'm super excited to actually present to you what's known about this field. So we'll have a rather relaxed talk. I'm not going to go super into technical details, though we would have a couple of definitions here and there. So just stop me at any time and we can talk about anything you want to. Okay. So let me first give you some very simple cues about what is happening. So, all right, we want to show that there are functions that you cannot compute in log time, right? So basically that there are some functions that are not parallelable as much as possible, basically, right? So in the perfect world, it would be just absolutely amazing if we can take any function that is polynomially computable, put it into a parallel processor, and in log n time, we'll get the answer. So because we hate fun, we of course want to prove that it is not possible at all. So in other words, that p is not equal to NC1. Yeah, so basically this is the main motivation of this whole line of work is to prove that p is not equal to NC1. That motivated the original definitions and everything after that. So this is a holy grail of this area. So yes, first of all, we have Boolean formulas. We have variables at the top. We have OR and gates, and they form this kind of tree that is used to compute a formula. So because it is very hard to argue for any low bounds for algorithms, we will be talking about low bounds against formulas rather than algorithms. And to talk about parallel computing, we need to talk about depth of the formula. So D would be the minimal depth of the formula that computes a function f. So to prove that p is not equal to NC1, we need to find, oh, sorry, that's a typo. We need to find a function f such that its depth is, sorry, that should have been omega of log n. So we need a function that has super logarithmical depth in the formula world, and because we can simulate any parallel algorithm with a formula of roughly the same depth, that would mean that this function is not computable by a parallel computer. But I'm making this argument about algorithm because I assume the main audience in this school is mostly interested in algorithm based on the lecture selections. So, but in my world, of course, the formulas and circuits are the primary object of the research, and I just focus on them exclusively. All right. So, what the Karchmer-Wigderson conjecture states is it's rather fascinating fact. Well, not fact, a conjecture. That if you take two functions and you compose them in this like block manner, so let's have this n times m bit input, and we partition it into blocks of size n, and we apply a function g to every block, and then we apply function f to everything. So we, after applying g, we will get the n-bit string, right? The m-bit string. So we can apply f, and we get this f-composed g function. All right. So the conjecture states that the depth of the composition is roughly the sum of the depths of the functions we are composing. and the roughly might be something you not see too often in the conjectures, but that doesn't mean like minus little or something, rather about 6 different definitions of what this roughly can mean, and all of them have one thing in common. They all imply that P is not contained in NC1. So apply this conjecture actually implies that P is not equal to NC1, which is incredible. And few more things. This way is it is not, we don't know obstacles on this path to proving that P is not equal to NC1, because if this conjecture is true, we will actually get the very concrete function that is computable in P and not computable in log depth. So there are no like natural argument. It's not natural in Rasborov sense. It's not algebraization. It's so all those barriers that we are aware of, they all do not apply here. So this seems to be like the way to go, because we currently don't know why this wouldn't work. So either we should come up with some argument why there is something wrong with this idea, or I think we should just all focus on proving this, because that's the way to do it. Okay. So problem is the formulas are all again hard to argue about. It's already better than algorithm in terms that it has like formulas as an object have this combinatorial structure. We have trees, we have symbols on them, so we already can count something, we can transform it somehow. It's already a lot nicer to work with than algorithms, but we can go in further and use the Karchmer-Wigderson games. So what is Karchmer-Wigderson game is you have this function f from n bits to 1 bit, and we have 2 players. One is given the x such that f of x is 0, and the other player, Bob, is given y such that f of y is 1. And what they need to do, they need to find an index such that the inputs are different in that input, in that index, right? So xi is different from yi. And of course, this thing should exist, because otherwise x would be equal to y and f of x would be equal to f of y, and we know that's not true. So communicational problem for the function f called Karchmer-Wigderson relation for f, or Karchmer-Wigderson game for f, is exactly this, right? So players are given inputs, they need to find an index using as few bits of communication as possible. And we can now reformulate the conjecture that so the why this so nice to work with, because the minimal length of the Karchmer-Wigderson of the protocol for the Karchmer-Wigderson game for f is exactly equal to the depth of the shallowest formula for f. So those 2 things are basically identical, and they actually correspond to each other quite nicely. We can take a protocol for the game and immediately convert it to the formula, or we can take a formula and immediately convert it to a protocol that solves Karchmer-Wigderson game. So, and the conjecture now that we can take basically we can formulate the same things in terms of communicational problems rather than functions. So that communication complexity of composition of 2 Karchmer-Wigderson relation is roughly equal to the sums of communication complexities of the games. All right. So let's take a look first of all how do we solve composition of Karchmer-Wigderson games. So suppose we have our inputs X and Y, right? So that we want to apply, again, the composition first goes by taking the inputs that like x1 to xm that corresponds to the rows of those matrices, and applying G to them, so Alice will get a vector A, and Bob will apply G to the rows and get a vector B. So now if they apply F to them, they will get 0 and 1, which are different. And they need to find a bit of a difference between X and Y. So anywhere in those matrices, they can do whatever they want, and they need to find a bit of a difference. So how can we solve this game? So of course, like the obvious solution would be just let Alice and send the whole matrix to Bob, and he will just tell her where is the difference. But of course, there is a more efficient way. So we can first solve the Karchmer-Wigderson game for A and B, find a bit of a difference. So then we know that G is different if applied to this row to the row of the matrix X and to the row of the matrix Y. So we can just solve the Karchmer-Wigderson game for G and get a bit of a difference. So that proved that the upper bound, right? So that complexity of the composition of two games is at most the sum of the complexities of the games. But what we want is to prove the other way, right? But it's a bit tougher. Okay, and a lot of the whole first section of this talk is about scaling down our ambitions just a bit, or getting like a simpler problems to work with. So we started with algorithms, said, okay, we don't know how to deal with algorithms, so let's go to formulas. And then we're like, okay, we don't really know how to deal with formulas, let's go to communicational protocols. And then we're like, yeah, that doesn't help either. So let's stick with this model, but let's now go change. Our goal is not to prove anything about functions. Let's focus on something that looks like a function, but is actually not a function. And this is called a universal relation. So universal relation is this, like Alice and Bob are given two n-bit strings, X and Y, and they need to find a bit of a difference. So far is the same as Karchmer-Wigderson game, but instead of having some function that is that differentiate them, right? We have just the promise that X is different from Y. So yes, or we can show it in another way. We can say, so there are two different definitions. We can either say that we have a promise that X is different from Y, or we can say, hey, also you can just tell us that just output some error symbol if X turns out to be equal to Y. And obviously, if we can solve this UN problem by some short protocol, we can solve any Karchmer-Wigderson game for any function, because it has all the Karchmer-Wigderson games as a subset, right? So it dominates them. But of course, there is no efficient protocol for this relation. So it's basically equality. It's even harder than equality in some sense. But we will use this universal relation as this like model object that is, again, something like a function, but not quite, but performs in a very similar way to a function. So things are getting a little trickier if we consider composition of universal relations, right? So now we're having this. So remember, the universal relation was this thing that kind of encapsulates all of the Karchmer-Wigderson games. So composition of universal relations would try to encapsulate all compositions of functions, as its subset. So composition of UM and UN is a game where both players are given a vector and a matrix. And we think of this matrix as an input, right? And a vector as as if it was produced by a function applied to rows of the matrix. So we have this AX and BY as inputs of the players, and the need to find a bit of a difference between matrices. So we need to find IJ such that Xij is different from Yij. Right? Okay. What makes it, again, composition of universal relations is that we have this additional promise that first of all, A is different from B, like before, right? Before we had that X was different from Y, now we have that A is different from B. And we also have that if 2 bits of a vector, so AK is different from BK, then corresponding rows of the matrix would also be different. So it would be a little easier to illustrate with a picture. So we have now a matrix X, a vector A, matrix Y, and a vector B. And the only thing we have, so they are not connected by those functions anymore because there are no functions in this problem. The only thing we know that A is different from B. So how can we solve this? How can we find a bit of a difference between X and Y? Well, we can use the fact that if AI is different from BI, then the corresponding rows are different, right? And then we can solve a universal relation on the vectors. First, find a bit of a difference, and then solve the universal relation on the rows of the matrix. So in this sense, the protocol for it kind of has this feeling of what the composition of functions is doing. So we have the same thing going on. And the question was, can we say something at least about this? And lucky for us, we actually can. We actually can prove a bunch of stuff about it. So first of all, there was 2 different papers, and there was something weird going on with the years, because the Impaliatas papers was the first, but the Hastad's paper was published first. So yeah, so they both proved by 2 very different techniques that the composition of 2 universal relations, so the protocol we just described, is essentially optimal up to the very, very small factor, right? Then there was kind of nothing going on for 15 years, and most people, the hope for that kind of faded away. And then there was this breakthrough by Gawinski, Mayer, Mainstein, and Wigderson in the 2016, who proved that actually composition of a function with the universal relation requires the log of the number of leaves for the function f. So basically, this is basically the depth of the function f, right? With a small factor at most, but yeah, plus n. So they proved that if we have not just vectors are not just different, they're different. We have this function f that differentiate them. We can still prove that the protocol is essentially optimal. And then there was our paper where we proved that, and that's a tricky part. So the Gawinski, Mayer, and Wigderson paper proved that for every f, we could prove that there exists a function g such that the composition of un with a g requires at least 1.5 n. So it's not it's not ideal in terms of the parameters, right? So we have not 2n, but only 1.5, and we have this weird quantifier that it's not for every f, it's there existent, or not for every g, but there is existing g. But lucky for us, it's actually the regime that is sufficient to prove that p is not equal to nc1 if it was not for un composed g, but for un composed f. So if we can prove that for every f there exists a g such that the composition requires at least the complexity of f plus epsilon n, that would be sufficient. So the regime is right, but the un is what's not great about it. Okay, so let me give you just a quick sketch of what the Impaliazza's lower bound was. So there are a few steps, but the main idea was that we have in the universal relation we have inputs that we can give to both players. That is extremely not what's happening in the real Karchmer-Wigderson game for functions, but we have to take advantage of what's given us, given to us. So yeah, so we're going to use this kind of weird property of this communicational problem to tackle it. So what we're going to do, we're going to go down the protocol by a path that preserves as many inputs that could be given to both players. So basically, we are maintaining the symmetry. I'm sweeping a little bit under the rug there, not measuring just that. They have a little bit more complicated measure of what the quality of symmetry is, but that's basically what's going on. And you do that for about n minus little o of n bits of rounds, right? And then you need to notice that if you have still like a lot of input that could be given to both players, we couldn't have been communicated about every row of their matrices a lot. There was no way to send a lot of information about each of the rows. So there are some rows that are not talked about, right? A lot at least. So basically, like this very boiled down argument is that if we have this n bits of communication, then we talked on average about 1 bit about every row. So there is like one row that we basically haven't talked about. Okay, so then we need to force players to actually find a difference in that row. So we need to show that the protocol would only be correct if it would output the difference between that particular row that we haven't touched much. And then you show that because there are still like a lot of options for that row for both players, it still would require roughly n bits of communication to find that bit of a difference. Okay, so that was the Impaliazza strategy. And now let's go to the second proof. It's actually quite funny because the measure argument was first introduced by Hastad and Wigderson for the UN composed with UN, and they had this insanely complicated measure that they used to prove it. But the thing is, if you find how to formulate that measure in just like a couple of lines, you immediately would get that that measure can be used for F composed with UN, and I have a feeling that's exactly what Gavinsky and Mayer and Wigderson did to prove that. So for F composed with UN, you need to find a good, some measure of a rectangle. So we have inputs of Alice, inputs of Bob, they form a rectangle, and we have this measure that will quantify the complexity of this rectangle. And we show that this measure is not reduced by a lot after each round of communication. So at least there is one message by a player that doesn't reduce this measure by a lot, right? So then you need to show that this measure was quite high at the beginning of the protocol by just computing the measure of all possible inputs, right? And then you need to show that at the end of the protocol, at the leaf of the protocol, this measure couldn't be too big. That's in their paper, that is basically where all the work is. They have this rather complicated measure, but the upper bound on that measure, this is where the real work starts. And if we do that, well, we have a large measure at the beginning, we have a small measure at the end. The measure was not reducing too much at each round, so we must have had a lot of rounds, right? So that's the whole argument. Again, the whole work is actually finding such a mu, but the idea of the proof is rather straightforward. So why I'm so very optimistic about this this area is that in our proof for UN composed with G, we actually used the symmetry argument. So we actually use it in even more straightforward way than in the Impagliazzo paper. So we just took all the inputs of Alice and Bob and we say, hey, just go down the protocol, look for the largest possible intersection of their possible inputs, and after n-3 rounds, you will end up with a rectangle that is still symmetric enough, and then you prove that on that rectangle you still have a lot of work to do. Okay, so hopefully in 15 years, or maybe hopefully a little less than that, we can actually find a good measure to substitute the symmetry argument with, to swap the UN for a function. Because the measure thing and the symmetry thing are doing basically the same thing. So the symmetry between two sets is a very simple way to say that they are that they look the same, right? So because they're the same, they have large intersection. If you discard everything else, we have two sets that are big and they look identical, right? And what the measure is used for is to say that, hey, we have these two sets and they are not the same anymore, but this measure quantifies how interchangeable they look for us, how hard it is to distinguish between them. So basically we're swapping this largeness argument for distinguishing argument, right? So this is the main idea. So basically it goes, it's everywhere. So instead of using large set, we can use a pseudo-random set, and this is the same type of argument. So use measure to quantify the basically pseudo-randomness of the difference. All right, so that is my absolutely main message of this talk. Basically, if I were you, I would drop like whatever you're doing right now and just focus on that, because I truly believe that this is a way to prove that P is not equal to NC1. So, and the last thing I wanted to talk about is this, is basically this artifact of our technique that was talked talked a lot before that when we're talking about functions, it's hard. So basically, how would you prove that for some function the composition of un with g is hard? And well, you don't really do that. What you do is you consider this like multiplexer game. So in this initial definition, it's rather weird. So Alice is given some function and an input, and if you apply the function to this input, the result is 0, and the Bob is given the same function and the input, and if you apply the function to the input, the output is 1, and they need to find a bit of a difference. And there is a folklore wrong proof that if you can prove a lower bound for a multiplexer, then it will prove that there exists a hard function. And the proof goes as following. So Alice can just take her input and start the protocol for G, right? And Bob will also start the communicational protocol for G, and they will execute it. And if G had a small protocol, then they will find in the bit of a difference, and that would be the answer for the game. And if for every G we had a small protocol, we will have a small protocol for multiplexer. That means that if multiplexer doesn't have a small protocol, then there exists a hard function. So the problem with this proof, while it looks really good, is that your protocol should be correct regardless of the promise. So for every pair of inputs, your protocol has to be defined. It might not be correct, but it has to be defined. So basically, if Alice's protocol is suggesting that she should go first, and the Bob's protocol for some other function suggests that he should go first, they would both kind of try to send a message which is forbidden by the model. And this, while those pair of inputs can never be given them, right, as a valid pair, because it violates the promise that G is the same, the protocol should be defined by the definition of communicational protocol. So this proof is actually wrong. And so to illustrate a little, to see it a little clearer, we can have this like non-promised version of multiplexer where they have functions and they either need to find a bit of a difference or just say that the functions are different, right? And in this case, all pairs of functions are all pairs of inputs are plausible pair. They're all permitted, and now again and those two functions, the two functions have the same complexity up to additive log n factor. So basically, what we want to do, we want to prove lower bounds for the multiplexer relations and the composition of multiplexer relations. So in our work, we actually consider the composition of a universal relation with a multiplexer, prove the lower bound, and then try to extract the hard function. But again, we have this roadblock that you cannot extract hard function from a multiplexer because it just doesn't work. It feels like it should work this way, but it doesn't. And there were few ways to deal with it. There was a paper by Ormeyer that say, hey, this proof actually works for the model where Alice and Bob talk the protocol is alternating. So first the first message is always by Alice and the second one always by Bob, and so on. But this is not a very interesting, in my opinion, model. So we wanted to do something for the real deal, right? For the real communication complexity. So to do that, we did something horrible, and we introduced what we called a half duplex communication complexity. And again, the only thing is that the only thing why it is here is to get around that particular roadblock of how to extract hard function from a multiplexer relation. So we have this model, Alice and Bob, they communicate over a half duplex channel. So at every round in classical communication complexity, they should know at the start of the round who is sending the bit and who is listening. But in this model, they both can do whatever they want. They can send 0, they can send 1, or they can just receive a message, just listen. So think of that as Alice and Bob can, they just have a walkie-talkie, so they can either push a button and say something, or they can listen. If the button is pushed, they don't hear anything. So, and then we have a classical, 3 types of rounds. We have a classical round where one is sending and the one is receiving. And then we have this like weird one where they're both try to send and it's just wasted. No one is listening anything. They're just yelling at each other. And they have a silent round where they both receiving. And in our model, we have this adversary who is choosing what they're hearing. So basically they're hearing some random noise over the radio and they have to be prepared to be correct regardless of that noise. So you can always prove that the communication complexity of the function is at least the half duplex communication complexity of the function, because you can always simulate the classical protocol with a half duplex protocol. And of course, you can just unravel the half duplex round into 2 classical rounds. So the first one where Alice is sending if she wanted to, and the second one where Bob is sending if he wanted to, right? What is curious about this is that we actually can prove lower bounds for this model, and the most important one is the lower bound for equality, where we can prove that you need n over log of 2.5. For God knows why reason, I never wanted to see this constant in any particular formula in complexity theory. An open problem is to either prove that complexities, half duplex complexity and the actual complexity, communication complexity, are the same, or provide an example where they differ by 1 bit. So we don't know that. We don't know if those models are actually different. But because we have the lower bounds, we can actually prove lower bounds for multiplexer relations or for compositions of multiplexer relations in half duplex models rather than classical. And then from there extract the existence of a hard function, right? Because now we don't have that roadblock, because that proof that I told you was wrong, because you can do illegal stuff. There are no such thing as a legal stuff in a legal round in the half duplex model. It's chaos. Anyone can do whatever they please. So that means that if we have a lower bound for the multiplexer in half duplex model, we can say that there exists a function that is at least as hard as a multiplexer, like minus some very small additional factor. And yeah, so this is a protocol. This is a proof, right? So if for all functions we had depth at most d protocol, then Alice just starts the shortest protocol for f, Bob starts the shortest protocol for g, and then they check that what they got was indeed the correct answer. And if the answer is incorrect, they report that they were given different functions. That's it. And we actually have tools, right, to prove lower bounds for this model, as I told you. And yeah, so what I encourage you to do is to consider composition of multiplexer relations, find a good measure, show that this measure doesn't reduce too much after 1 round of a half duplex protocol, right? So this part is usually very simple for the normal communication, and could be quite tricky for the half duplex. Sorry for the typo there. And then you just need to show lower bound and upper bound on that measure at the different points of the protocol. use that to prove existence of a hard function and show that p is not equal to NC1. That's the plan, and yeah, that's it. That's all I have for you. I think that's a good place to stop.
Yeah, thank you very much.
Thank you for the lonely clap. I appreciated that.
Yeah, well, it is hard to do claps in online mode. Yeah, sorry. Any questions so far? Let me stop the recording at this moment.